Last time we started talking about critical points. One more time, well, from the Calculus 1 class. At the same time, I'm teaching this week critical points in my Calculus 1 class. Calculus 1 taught us that critical points are points where the derivative is 0 or d and e. But we have now more than one derivative. We have partial derivatives, as many dimensions we have. So now you have to take partial derivatives and collect them together. That was the definition of critical points. And we were asking you, find the critical points of this function. That is a gradient. Your homework right now is about gradient. This is a new sign, upside down triangle. The gradient is a collection of all the partial derivatives. You find them, you set them equal to 0 in d and e to find critical points. And you will have couples, many couples of points. In this case, it was only 1 point. So we found some critical point. And then we realized we don't know what it means. And that's where the second derivative test comes in to help us to analyze. The critical point is a candidate for local minimum and local maximum. So we need to know the second derivative test. Yes? I will check. 11.7, yeah? Yes, 11.7. That was a hard question. Surprisingly, I did not expect that. So it's 11.7. Second derivative test says find the determinant and collect all the partial derivatives in that determinant. Fxx and fyy and a diagonal. The first row belongs to x derivative, so fxx, fxy. The second row belongs to y derivative. And then the third row to the z derivative, the fourth row to the m derivative. And it's the same thing. 2 by 2 matrix, 3 by 3 matrix, and so on. For now we do 2 by 2. So we did that. We found all possible second derivatives, x, xy, yx, yy, and created this beautiful determinant. So why did we do that? To apply second derivative test. The thing is, this determinant will now help us to identify if the critical point is local minimum, local maximum, or a third type, which we don't know yet. 2D was pretty straightforward. In 2D, we were teaching you if there's a hill, the derivative here is 0, or maybe D and E, right? And this is your possible critical points that give you global or local maximum. Same here, minimum. In 3D, now there's a third dimension. This is a shape in 3D. We will have a new shape, which will be maximum and minimum at the same time. Until I will give you away what's the name of that. Try to visualize what kind of point can be maximum and minimum at the same time in 3D. That's a pretty cool idea. But before we go that, let's finish some algebra. Who knows how to calculate the determinant of 2 by 2 matrix? It's fine if you don't, because I will remind you right now. We taught you how to do 3 by 3 just recently. It's actually the same idea. You choose this, it bombards, minus, but there is an easier way to remember it. Cross multiplication with a negative sign, cross product minus cross product. 12x squared times 12y squared minus 0 times 0. Smiley face. So this is the formula. Here it is. In case you don't remember, it's the determinant of the 2 by 2 matrix, just cross product. Let's simplify. 12 times 12 is what?
144.
144, thank you. X squared and y squared. Put it in the box. For now, we don't really know what it means. The thing is, we were asked to find not this. We were actually asked to find this determinant at a particular point. And the particular point was 1 and 2. Oh, we don't have it here yet. I see. So it's actually easier to first plug 1 and 2 and then calculate determinant, then whatever I just did right now. So plug 1 and 2. X is 1. Let's use a pencil and write it down. X is 1, y is 2. Then it becomes 144 times 1 squared times 2 squared. which some kind of number. So there's a suggestion, actually probably it's easier to plug numbers first and then do the cross product. Possible, then D at 1 and 2 will be 12x squared is 12 times 1 squared, so just 1. 0 is 0, 0 is 0. 12y squared is 12 times 4, 48. See? And the number will be 12 times 48. Should be the same number. 576. 576. So this also should be 576. So either or, either you calculate it and then you plug the number, a point, or you plug the point and you calculate. It seems like it's easier to plug the number because what if this number makes everything 0? That is more convenient. Why there's a number? Because we check in a particular place if the derivative for this place gives you maximum or minimum. What does this mean? So this is the question we're going to answer today. The second partial second derivative test says this. So you need to write down this idea. You find the derivative or partial derivatives, and where are they? Zeros or D and E's, or D and E's for sharp corners. Then you build this determinant. They gave you formula here. I usually don't remember the formula. I remember the determinant form. D is, and you know you have all the partial xx, xy, yx, yy. So that's what they say. Of course you can memorize the formula, but I think it's too much memorization. A visual determinant is easy to visualize. But the most important and a new thing is now what does it mean? If determinant is 0, positive, greater than 0, if that number we just found, just a sec, is positive, then we need to do extra step to figure out if it's maximum, local or relative maximum, or local or relative minimum. If it is negative, then we have a new third type of maximum and minimums, which are neither or both at the same time, called a saddle point. If D is 0, then just like in calculus 1, we say choose another test, no info. No info. So I will leave it for you right now to write down and answer the questions. Yes? Sorry.
Can we see an example of what a saddle point looks like?
Yeah, it's literally right below. I'll show you in a second. Yes?
Perfect. Thank you.
The previous example that you did,
What?
the previous example that you did, where did you actually get the 1?
1 and 2? Yeah, I realized actually I never mentioned. Oh, it's here. 1 and 2.
Using the same, okay.
It's the same example. We're just following. Find the critical points. 1 and 2. Yeah, that's how we're using it.
The point that we found.
Yeah, the point we found. That's the critical point. Let me point it out. I like that she mentioned this. This is a critical point. We used critical point. We found it. It was never given. And this is critical point. Thank you. It's a good point that you said that. Critical point. Or else it doesn't make sense. We found it. We're building second derivatives, putting them in determinant, finding that number, but where? At the critical point. Second derivative test tells you to build this determinant and plug in this a comma b, where a comma b are critical points. So let me write down a comma b are called critical points, which means derivatives, partial derivatives at a and b are 0 or d and e. Yes, there was a question. So saddle point, very interesting. I have several cool animations to show you. Maximum and minimum make sense. Here is in 3D. Maximum and minimum. Saddle point, very interesting idea. If you imagine a saddle on top of the horse, on horse, then it is maximum from the point of view of your legs. So your legs are swinging below, and then you're sitting here, so it's maximum for your legs, but it's minimum for your body. That is pretty cool. At saddle point in 3D, it's both maximum from this parabola point of view, but minimum for this parabola point of view. So it depends from which dimension you're looking at it. X size dimension or Y size dimension. Here's more visual. It's a chip, if you remember, right? It's a chip. So a saddle in 3D is exactly perfect shape for chips. From this parabola point of view, this is minimum. From this parabola point of view, this is maximum at the same time. Pretty cool idea. So here's some visualization. If you drop a ball on top of this saddle, where really? It's not the first time happening.
Aww.
Let me make sure. Any? Okay, Wikipedia should work. Okay, good. Well, okay, that's not a saddle. This one actually has a saddle, but it has also minimum and maximums. We are looking for maximums, which are these heels in 3D. We are looking for minimums. This is where the balls will stabilize. This is somewhere minimum over here. This is a saddle point. It goes like a saddle shape, like so and like so. Pretty interesting. And then, but it was such a good image. Okay, that was easy to find. Saddle point. So I will show you. Luckily, that's the easy one to find. Here it is. If you drop a ball, in this case many balls, on the top of the saddle point, some of them will go down because it's maximum, and you slide down from the maximum. You slide down because it's top of the mountain. Some of them will stay because it's minimum. It's the lowest point from the other point of view. How cool is that? Do you see? So whoever stays from there, if this is humans, they will tell you, oh, I'm at the minimum of some kind of valley, right? Whoever just slide it down, they will say, no, that was the maximum over there because I just came down. So it depends from which point of view you're looking at it. And that's a pretty creative idea.
Smart people float in the air and take the saddle point.
Yes. So you are now a smart person. He says you are all wrong or right at the same time. This is called a saddle point.
So then, would any point between two hills be a saddle point?
No, good question. So no, you will see later. That's a critical question. Not all points between are saddle points. Same visualization here. So now let's learn what second derivative test tells us to do. The second derivative test tells us if this determinant we just found, so we continue the same example, negative, you immediately going to get a saddle point. But if it's positive, it will be one of these two, and we will have to continue investigation to find which one it is, local maximum like here or local minimum like here. So let's do it. We keep going with the same example. We found that D at 1 and 2, which was a critical point, is 576, which is greater than 0. Thus, so let's do note number 1. It's not a saddle point, not a saddle point. Then it's either maximum or minimum. To identify which one it is, we will have to do one extra step. The extra step requires us to calculate one extra derivative at the point we found, 1, 2. Check. So step 2, check f(x)(x) at 1 and 2. So that's what the second derivative test tells you over here. If x, only xx, the second derivative with respect to x and with respect to x, is positive, then it's minimum. If it's negative, then it is maximum. I will tell you in a second how to memorize it. Black. So let's figure it out. Check this number. So I need to go back and figure out what was my second derivative. Second derivative, we have it in our notes, so we don't have to recalculate it again. The second derivative of x and x was 12, was it x squared?
Yes.
12x squared, thank you. So at 1 and 2, I just need only to plug 1. It will be 12. 12 is positive. So both determinant was positive at the point we found, and f(x(x) is positive at the point we found. This gives us the conclusion. Thus, by second derivative multivariable calculus test, this point is local minimum. The critical point we have to locate, 1, 2, is local minimum. In calculus 1, I teach a funny way to memorizing it. If the second derivative is positive, and in this case it's positive twice, determinant is positive and then f(x(x) is positive. The face is smiling, and when the face is smiling, it is minimum because the tongue of the smiley face is at the bottom, so that's how you should memorize it. Well, that's how you can visualize it. If we got positive determinant but negative f(x(x), so this is f(x(x) and this is determinant, then it's grumpy. And since it's grumpy, the nose is local maximum. That is a very childish way to explain it, but I think students like it, so. Maximum. Like so. So in calculus 2, in calculus 1, they were both negative because it was just second derivative. Now we have two tests to check. Find d first and then find xx. So, local minimum. The answer is, final answer. Final answer. There is a local minimum on this 3D shape with mountains and valleys and everything. A local minimum at x, y equals 1, 2, which is f of 1, 2 is negative 37. Who knows where did I get this from?
Is it the original?
It is from the original. Usually, if you remember in calculus 1, we ask you to find a critical point to classify it. And that's what we're going to do. We're going to ask you to classify it on the second exam. The critical point, we'll figure out its local minimum, but then we want to know how low does it go below the sea level, for example. It goes minus 37 units low. Actually, it goes 37 units low. So either you say minus 37 or you say 37 low. You don't say both. Yes. Questions? So I plugged into the original. The last step is always the same. You plug into the original. Here's a nice diagram. You don't have to memorize it or copy it. It actually makes sense. You find critical points, zeros in D and E, partial derivatives, all of them. That gives you a list of points. You build your D, which is determinant. If the D is negative, that will conclude your progress of classifying the points. If it's negative, it's a saddle point. It was a funny way to remember. Negative, very sad, so it's saddle point. Fine. If it's positive, you have to do an extra step. Find f(x(x). Now, if it's positive and positive, it's a smiley face, so it's the minimum, the bottom of the smiley face. If it's positive and negative, then it's maximum. Kind of this idea. Saddle point is like very, very sad. That's why it's saddle. Maybe like English kind of way to memorizing it.
Question.
Yes?
Why do you use the partial derivative xx?
It comes from the theorem.
Oh, okay.
It comes from the theorem that if we don't know, we now definitely know it's not a saddle point. It's either maximum or minimum. How to check which one? The concavity of the concavity. So xx will tell us if it's smiling in three-dimensional way, so like a cup, right? Or it's upside down cup. Then it's maximum. But it comes from the theorem. It's a good question. She just asked why only xx theorem and the proof of the theorem. Yeah. Bless you.
So if it's a sub,
You see, means I said the truth. Do you remember? Who remembers this joke? Russian joke. If someone sneezes, means whatever I just said was true.
I
Yes.
said that like on the first day of class.
Yes, I said it in every class. Yes.
If it's a saddle point, then we just stop.
Then we stop. So the whole problem has a title, classification of critical points. There are three cases. Either it's a saddle, remember the course in the saddle, or it's a maximum, remember the top of the 3D hill finally, or it's a minimum, which is the bottom of the 3D valley, yeah?
Well, we've had examples where like we get multiple critical.
Let's do it right now. Thank you very much. Let's have example with all the three cases. You asked for it, so now I have. If you find this process is kind of weird, it is true because in general we don't really do that. That's just a side note. In general we use eigenvalues and matrices to do this kind of stuff. Take linear algebra class and you will enjoy the easier process. I did my master's degree with eigenvalues, so I do know that kind of stuff quite well. But yeah, usually we don't do whatever we do here. But it's an upper level class, so to get into eigenvalues you have to take linear algebra. So here is a nice visualization. What do we do? Local maximums, local minimums, and here's a saddle point. Look at that. Here. See? Maximum from this point of view, but minimum from this point of view. Pretty interesting. Let's do the example where we get everything. This is going to be on the test, okay? Or the quiz, or both. Find the local maximum, minimum, and saddle points, if there are any. Guess what? There are all of them. So this example is an amazing YouTube video right now, how to find all points. Let's do the process. Step 1, solution. Step 1. Find critical points. Critical points already have some kind of trigger in your brain, means derivatives. But we have many variables now because it's a multivariable calculus. So find all the possible partial derivatives. If there are 5 of them, 5 variables, find 5 partial derivatives. But since we're being easy on you, it's only 2. F with respect to x is 3x squared minus 3 plus 3y squared. Too fast, or do you agree with me? See, x is a variable, y is a constant. What if the derivative with respect to y? 6xy. This is correct. 0 minus 0 plus 3x stays. 2 goes down. 2y to the 1. So the faster you can do it, the better. We found these 2. Nice. But the goal is to find critical points. We need to solve this for 0, zeros, and d and e's if there are any. As you can see, we don't bother you with fractions, so there will be no d and e points. Polynomials are all continuous. There will be no, we call them singular points if they're bad points. D and e points, singular points, they're only stationary points. Let's solve the first equation. Is complicated. So let's do the second one. 6xy equals to 0 gives you 2 possible solutions. Either x is 0 or y is 0. Make sense? Those are critical points. Because product of 2 gives you 0, so either or both. Right? Now, how about the second equation? So now, this is the interesting idea here. You already have one x. This x can now be used to plug into this equation to find the y that belongs to this x to complete the couple of the point, because point is the pair, right? So, step 2. Step 2. I will have 2 cases. Case when x is 0. Plug into f sub x. What is happening when I'm plugging when I plug 0 into f sub x? It will be 3 times 0 squared minus 3 plus 3y squared, and this must be 0. That's what we're solving for. So we're going to have minus 3 plus 3y squared equals to 0. Because this is just 0. Makes sense? Keep solving for y. 3y squared equals 3. Y squared equals 1. Divide by 3. y equals 1. Yes or no? Plus or minus. Don't forget, please. Plus or minus. There's some kind of little panda is crying when you forget minus 1. So don't forget.
Not the pandas.
Yes. The pandas. So now we have 2 points from plugging 0. We have 2 critical points. 0 and plus 1, 0 and minus 1. Just from the first exploration, which I called case x equals 0, case 1. But we have second exploration to do, case 2. Y equals 0, then what is the corresponding x for that? And you repeat the whole process. It's still step 2, but it's now case that y is 0. Let's see if that gives us different solutions. You plug into the partial derivative for x, because we found it from the partial derivative of y, so we don't use it anymore. That will give you 3x squared minus 3 plus 3 times 0 squared. And this must be 0 in order to count to be a critical point. Solving 3x squared minus 3, because this is 0, gives you 0. And you have the same situation, x equals 1, x squared equals 1, x equals plus or minus 1. No panda is crying today. So there are 2 points from the case 2 as well. Let's put like a bullet point. Bullet point here and a bullet point here. There are 2 points from this scenario, but now they are 1, 0 and minus 1, 0. So in total, how many critical points did we find? 4. There are 2 critical points from the case now 1 and the 2 critical points from the case 2. Critical points, and we have to check them all. Catch them all. Minimum maximum saddle point, or none of. Maybe sometimes it's just fake candidate. You remember they are candidates to be oh, I don't have space, okay. They are candidates to be maximums or minimums or saddle point. Step 3, check these critical points. They are called candidates. Yeah. Oh, zoom out. Thank you. How do we check? We check using second derivative test. Second derivative test told us create determinant, plug the points into it, see the sign. And now let's remember, if the sign of determinant is negative, it's set, so it's saddle point right away. If the determinant is positive, you have to do the extra step. Find fxx at each point. If positive, happy face, minimum. If positive, negative, sad face, maximum. 3 cases, and we have to go through them all. So, let's do it. Candidates. Let's find, we need to build determinant, right? Which is second partial derivatives in order. But we don't have second partial derivatives, so we need to find them, right? And this is where it's nice if you put the first derivatives in the box. Or you can copy them one more time just to have them, why not? So, I kind of don't want to, but okay, let's do visually here like so. We had f sub x was 3x squared minus 3 plus y squared, and f sub y was 6xy. Now you can build it right away. You don't have to do the whole list like we did in the previous homework. Just build it right away. Fxx, which means look at the f sub x and differentiate one more time with respect to x. It will give me 6x. Done. Look at the same line, but now differentiate it with respect to y. It will give me 2y. Amazing. Now switch to the second line. I mean this number line and 1 and number 2. f sub x with respect to, no, f sub y with respect to x will be 6y. So be careful with that. And now y. Second line, but with respect to y is 6x. This is amazing job. Questions? Did you get how we do it? Too fast or you're fine? This is like knowing partial derivatives from the previous quiz and classes. Yes.
So at this point, we could plug in
All the
of
points.
our critical points.
Yeah. So now, I used to actually calculate the determinant right now. It will be 36x squared minus 12y squared. But the suggestion says, let's plug all the points now into this determinant. Yeah.
Wasn't our partial derivative of x 3x squared minus 3 plus 3y squared?
Yeah.
So why did
Oh yeah, true. I lost the 3. I lost the 3. Then, what should I fix? This one.
Yeah.
Yeah, thank you. Good catch. Good catch.
Good job.
Now we have symmetry.
One more question.
Yeah.
Are the xy and the fyx, are those always supposed to be equal?
Good question. We had definitely, good job. We definitely had a theorem about this. If functions are continuous, and usually we look at the functions or curves or surfaces, which are, you see, continuous. They're smooth. There's no gaps with a waterfall. So like they're all smooth mountains. If that is the case, it is true that the diagonal should have the same results over here. So almost for everything, it's true they are going to be the same. But it's nice to check. Maybe, you see, I messed up this one, so I should have noticed that they're not the same. And like, okay, I messed up one of these. Let me check both. Yeah, good catch. Now plug the points. That is step 4. Step 4, you plug all critical points into D. And it's nice if you number them. So point number 1. And doesn't matter which order you go, but it's nice if you start numbering them, because if you have 10 points, you start losing the order. Let's start with 0, 1. D at 0, 1 is, plug the point, calculate your determinant. At 0, 1, maybe you have a pencil and write down x equals 0, y equals 1. It's going to be 6 times 0, 0, 0. 6 times 1, 6, 6. You see how simple is that? And now I'm multiplying cross product minus, with a minus in between. 0 minus 36 negative. We just need to know the sign. We don't care about the number minus 36. We just need to know if it's positive or negative. Since it's negative, you just said it. Good job. It's so sad that it is saddle. It's a saddle point. So that's actually a good luck if you get it on a test. If you get the negative number, you can choose saddle point and you move out. Now, point number 2. How many points do we have?
4.
4. Point 2. The second point is 0 and minus 1. Very fast. Plugging 0 and minus 1. Will be the same? Let me see. 0 makes everything zeros in the first diagonal, but minus 1 makes it minus 6 and minus 6, which gives me 0 minus 36. So it is
No, it's
Still negative 30.
It's still negative.
still negative 36. Good job. Because minus 6 times minus 6 is plus 36, but minus makes it minus. Funny?
I was just gonna say, if you were just to take the if you're just to multiply it out without putting the points in, it becomes a little bit easier.
I think so too.
So many points.
I think so too. The point that he's saying is, why not just calculate it right away? 36x squared minus 36y squared. That's what I used to do. But then some people claim that actually it's easier to plug first and then calculate, maybe with upper numbers,
Yeah, like
digitals.
way later, yeah.
Maybe when you have like 5 by 5, it's nice to have zeros everywhere, and then you start calculating, versus y. But yeah, you can plug it into this if you want, or you can plug it into the determinant. Yeah, both ways are good. So we have 2 saddle points already. That is lucky, because others have to have more calculations. Let's see what the others give you. Point number 3. Again, order doesn't matter, but you need to check them all. Yes?
For Why is the first one negative? And then why is
So
the
0
negative?
minus 36. You always do minus when you cross product multiply. 0 times 0.
The saddle point on the bottom be positive?
So 0
Positive and then
minus 6 times minus 6. Minus 6 times minus 6 gives you still plus 36. And then minus, so it's triple minus. No, it's a good question because it is algebra, and the more upper level classes you take, the worse you become in algebra. It's the law. It's always like that. Yeah.
I don't like that law very much.
Nobody likes it, but that's the truth. So, D at 1, 0 is, let's see, I don't remember what my D is. Here it is, 6x. So what are the zeros? Now the zeros will be on the other diagonal, right? 0 for y, make this 0 and this 0. 1 makes 6 and 6. That is 36. Positive. So we have to go and ask for help with the second derivative of xx at this particular point to understand if this is maximum or minimum. But this we know it's not a saddle point. So extra step is, let's change the color, fxx at 1, 0 will now determine if it's positive or negative. So I need to go back. I never actually wrote it down carefully. So I know it's over here. That's why I don't write it carefully, because I always remember it's the first corner thing. So it's not very necessary to write them down in order. You see, this saves you time on the test. You just remember it's the first corner. It's 6x, right? So 6x, let me put like so, a bar at 1, 0. Bar means at 1, 0. So it's 6 times 1, which is 6. When both are positive, I don't care about the number. When both are positive, visualize a 3D cup. It's a smiling face. A 3D cup. The bottom of the cup is minimum. So it is local minimum. Or you maybe remember it's also always the other way around. Positive gives you minimum. Finally, the last point. Point number 4. As you can understand, your homework will take time. So this, no, it's not a joke. Honestly, this last homework, homework of this chapter is time consuming.
Can you give us last question?
Let's check. D at -1 and 0 is zeros, because y gave you zeros. -6 and -6, still positive 36. So we do the same check with the purple color. With a purple color, go down. Fxx at -1 and 0 is, it's still 6x, so it now will be -6, which is negative. Negative makes a 3D, so it was positive first, then became negative. It's a grumpy face, so this nose is your local but 3D maximum. Remember, this is all in 3D, so I'm kind of supposed to make like a 3D cup, right? So it's a very sad 3D person and a very happy 3D smiling creepy face.
It does look like a clown.
Yeah, a little bit.
It reminds me of
Conclusion. Conclusion. Let's conclude. You need to list all of them. Besides, in my exams, you know, at the end, I like to have a summarization. So, yeah. No problem. Maybe I'm too fast, so you definitely should let me know. Final step. Let me check. What was the step? Step 5. Step 5. Summary or thus, whatever you like to use. I like thus because it's short. Conclusion. Conclusion is a professional way to say it. If you don't make typos. Conclusion. Okay, let's see what's the conclusion. F at 0, 1. You plug it into the original function, and I will do it for you. 0 cubed minus 3 times 0 plus 3 times 0 times 1 squared is 0. This is a saddle point. A saddle point. 0, 1 was a saddle point. I plugged it into the original to find how low or high the saddle point goes. There was one more saddle point. F at 0 and minus 1. I'm plugging in and I get height 0 as well. That is also a saddle point. So we have two saddle points, nice. And then we have maximum and minimum, so all possible examples. Here it is. I will change the color to green. F at 1, 0. If you plug into the original, you will get -2, and it is a minimum. Local 3D minimum. Always remember it's in 3D now, not in 2D anymore. Not a parabola kind of thing. It's a paraboloid. And F at -1, 0. If you plug into the original function, it gives you 2, and indeed it is a local maximum. So two saddle points, local minimum and local maximum. So it's basically a hill, a pit in 3D, and two saddle points, maybe between them or around them. Pretty cool idea. Yes?
So would it be accurate to say that points 0, 1, and 0, -1 are saddle points at height z equals 0?
Yeah.
And same with, the same wording with points 1, 0, and -1, 0?
Yes. So very good comment. Height, remember, it's a third dimension, so we can call it z, right? Z equals -2 or z equals 2. That gives you the height, the output on 3D up and down, minimum and maximum. And z level 0. At level 0, there's a saddle point. Very interesting. At height 0, there is a saddle point. Two saddle points. Yes.
Can we say like f of 0, 1, 0 is a saddle point?
F0. No, don't.
Point?
You want to merge into one notation?
Yeah.
No, don't do it. Definitely split into two. Is I understand correctly, you're asking F0, 1,
(0).
comment like so? Oh.
Yeah.
No, it's so I will answer like so. Let's go back to what function looks like. It looks like so. Z equals. Don't include the third dimension into whatever is already third dimensional, right? So Z is my height. This is my height, which is output, right? Output used to be up and down in 2 dimension. Now it's up and down in 3 dimension. This is my inputs, 2 inputs, left and right, which we call run, rise. But now it's in 2D on the floor. So I call it front and back, left and right, and Z is up and down. So we found the critical point in 2D. We classified it. Oh, this point on the floor. This point on the floor, actually, I'm standing on a saddle, top of the saddle of the horse. And then we found the height of that saddle. Height was 0, so horse is lying on the floor. And then, this point on the floor gives me local maximum. So apparently I am on a local hill. There may be more hills, but I'm the corner. Good question, yeah. More questions? Yes? I will check after class, okay? More question? He just asking about annotations. Yeah?
I have another one. So when you plug in 0, it was at the very beginning. When you got x equals 0 and y equals 0, when you said 6xy equal to 0,
Yeah.
if those were critical points,
Yes, they were beginning of the whole process. I chose a random equation, either this one or this one, to start. And the second one looked easier, so I chose the second one. From the second one, I found 0 and 0, and I started plugging them in here to find the corresponding couple for each.
okay, so you just
Yeah,
set one of them equal to 0,
yeah.
solve it, and then solve the point.
Plug in and still set it to 0 to solve for another one.
Oh, okay.
In any order you want.
Did we just spend the entire class on one problem?
I just spent entire class on one problem, so I will probably move this homework to finish, because we did not finish. We still need to learn to find distances between the plane and surface and global maximum on the closed interval. That we'll do it on Monday then.
Okay. Because I was like, if each question